Hello. Today we're going to talk about the structure of the Earth and plate tectonics. So let's get ready to discuss how the movement of Earth's plates affect our planet's surface. First, let's begin by answering the question, what are plates? Well, they're continental slabs that make up the crust and the mantle. Plates are constantly moving, but they're moving very slowly. If you look at the map of a world, you may notice that some of the continents could fit together like pieces of a puzzle. What was once called the theory of continental drift, where it was thought that only the continents moved, is now the theory of plate tectonics, where it includes the moving seafloor. Alfred Wegener hypothesized that the continents were once joined together as Pangea. This was over 300 million years ago, and eventually they drifted apart. Now, Wegener had several pieces of information to support his claim. One was look at the land features. Specifically, you notice that the continents fit together like a puzzle. He also noticed that with mountain ranges, they seem to match up between South America and Africa. He also noticed that there were coal fields that matched up in Europe and North America. Now, looking at fossil evidence, you could gather that the continents were once joined together because, if you notice from the image below, there were examples of fossils located in both types of countries. In one case, you might find one organism in South America as well as Africa, and you might even find some that were in Antarctica that were also found in Australia. So this evidence suggested that the continents were once combined, because obviously many of these organisms could not swim across the ocean. The Earth is divided into 12 major plates, which are moved in various directions. These fit almost like puzzle pieces and can slide just ever so slightly. Now, this plate motion causes them to collide, pull apart, scrape against each other, and a number of other things, which cause a number of tectonic events, which we will discuss later. Now, each type of interaction causes this characteristic set of earth structures or tectonic features. The word tectonic itself refers to the deformation of the crust as a consequence of the plates' interaction. And we'll talk more specifically about examples of those later on. Now, just from a general standpoint, plates can move in various ways. They can move away from each other, they can move toward each other, or they can move past each other. When plates actually move together, these can be used to form mountains or volcanoes. When plates move past each other, this can cause earthquakes. The image provided shows several of the tectonic plates across the globe. Notice that some of them align with the borders of continents, while others may be lined up in other areas. These all have the possibility of moving around, kind of like a jigsaw puzzle. Now, what are tectonic plates made of? Well, they are made of the rigid lithosphere. This is a hard portion located at the crust on the Earth. The lithosphere is made up of the crust and the upper part of the mantle. What lies beneath the tectonic plates is an area that causes them to move. Below this area is a plastic-like area called the asthenosphere. The asthenosphere is located in part of the upper mantle, and it helps provide movement of the tectonic plates. Now, once again, the plates of the lithosphere are moved around by the underlying hot mantle, which includes the asthenosphere. But the convection cells cause something called convection current, which allows these plates to move around. As indicated by the image, if you look, there are arrows that suggest in the mantle region that kind of move in a circular direction. As these arrows approach the surface or the crust area, or in this case, the lithospheres, which feature the tectonic plates, they cause them to move. In some cases, they can go underneath or they can go on top of another. Now, what happens at these tectonic plate boundaries? Well, as I mentioned, there are a lot of ways that the plates can move. Now we're going to assign specific names for what happens at these boundaries between plates. One is called divergent, one is called convergent, and the other is transform. So we have a total of 3 that I will discuss. I'm going to begin with discussing divergent boundaries. Now, divergent boundaries refer to boundaries that tend to spread apart. Classic examples of these occur where you have the spreading ridges. As the plates move apart, new material is erupted to fill in the gap. And there are classic examples of divergent boundaries that can be shown whenever you see something called a spreading ridge. Now, speaking of spreading ridges, there was a popular finding by a guy by the name of Harry Hess, and he discovered in 1960 that there was seafloor spreading that occurs in our ocean's bottom. Using navigation equipment, he was able to deduce that as the seafloor spread, the crust or the oceanic crust began to emanate and go in a lateral direction, either left or right, away from the point where it was coming up. Now, as it began to spread, what began to happen is new oceanic crust began to form. And as this new oceanic crust began to form, it began to spread. So, looking at the image provided, the colors depict the relative age of the rock. And in this classic example of seafloor spreading, if you look in the red regions, these represent rocks, or areas of rock rather, that are newly formed. And as you look to the areas where they are the green and it goes to blue, those represent the rocks that are much, much older. And so what happens is the red rock begins, and then it begins to spread laterally in the directions of left and right. And eventually it will become just as old as the yellow and the green and the other blue rock. And this process keeps going on and on. Now, there are 3 styles of convergent boundaries. And within these 3 styles, they include continent-to-continent collisions, continent-to-oceanic crust collisions, ocean-to-ocean collisions, and these refer specifically to the interaction between the types of crust. As I've highlighted, continent to continent, which presumably suggests that there are continental crusts that interacts with a continental crust, causing a collision. And continent to oceanic, there's an interaction and collision between both types of crusts in those cases. And then with oceanic to oceanic, you have an interaction between those types of crusts. So, continent to continent collisions can be used to form mountains. Such examples include the European Alps or even the Himalayas. In the case with continent to continent collisions, you have an interaction between the continental crust of one side and the other, and as they interact, one side of the continental crust ends up being pressed down while the other is slightly raised up. And again, that was how many of the mountain forms, such as the European Alps, as well as the Himalayas, were formed through continent to continent collisions. And here are some images of the Himalayas. Again, this is another example of continent to continent crust colliding to form a landform, in which case one part of the continental crust is subdued and goes underneath, and the other part is raised. Now, another example is continent to oceanic crust collision. This process is called subduction. In this case, you have oceanic crust which interacts with the continental crust, and the oceanic crust ends up subducting or going underneath the continental crust. As this occurs, you have the heating process, because in that crust area you have various types of rock that heat, and in the image provided you can see a classic case of how a volcano can be formed through this process. Here are classic cases, effects rather, of subduction. Here you see an image of a volcano or mountain formation. And again, the oceanic lithosphere subducts underneath the continental lithosphere. So again, the oceanic crust goes underneath and the continental crust goes above. Now, the oceanic lithosphere heats and dehydrates as it subsides. And the melt rises, forming volcanism. So an example of this would be the Andes Mountains. Finally, we have oceanic to oceanic plate collision. When two oceanic plates collide, one runs over the other, which causes it to sink into the mantle, forming a subduction zone. The subducting plate is bent downward to form a very deep depression in the ocean floor called a trench. The world's deepest part of the ocean are found along trenches. In fact, the Mariana Trench is over 11 kilometers deep, which is pretty far. I believe that's more than about 35,000 feet deep. And so in the images provided, you can see examples of some of the vegetation that are found in these lower parts of the water. Now, transform boundaries represent our third type of plate interaction. During transform boundaries, you have an interaction where the plates actually slide past one another. An example of that can be seen in the view of the San Andreas Transform Fault. Here you have the plate boundaries rubbing laterally one across each other in terms of edges. In the map provided, there are various examples of the plates and their interactions, and you can see clearly how these plates can actually rub with one another. Depending on the region of the plate, you can have any variation between oceanic to oceanic, oceanic to continental, or even continental to continental collisions. It just really depends on where that boundary is located. Volcanoes and plate tectonics. So what's the connection? Well, there's the Pacific Ring of Fire, and this is an area where volcanism is mostly focused and highly volatile. So this region is highly susceptible to volcanoes. Volcanoes are formed by subduction, rifting, and hotspots. Earthquakes and plate tectonics. What's the connection? Well, as with volcanoes, earthquakes are not randomly distributed over the globe. In fact, at the boundaries between plates, friction causes them to stick together. When built up energy causes them to break, you then get earthquakes to occur. So if you look at these spots, this figure shows where the distribution of earthquakes occur around the globe. And if you'll recall from the previous images of the tectonic plates, many of these distribution of earthquakes, if not all, are aligned with that of the boundaries between the tectonic plates. So here's an image to show those interaction between those plates to kind of give you a perspective as to how the earthquakes occur. Usually you have an interaction, whether it's the continental crust or the oceanic crust, and they have some kind of collision that causes this set of tectonic movement, which can at the end of the day cause an earthquake. So, in summary, there are three layers that you make sure you want to be aware of, and they include core, mantle, and crust. But most of the activity that we're familiar with occurs at the core and near the upper mantle. That being the case, as plate tectonics is the focus, we need to understand that these tectonic plates can move around, although very slowly, and the plates are made of the crust and upper mantle. Now, there are two types of plate, and there are three types of plate boundaries that we've discussed. And lastly, volcanoes and earthquakes are closely linked to the margins of the tectonic plates. And so that completes our summary today on plate tectonics.